So this module is what's called quantification theory, part 1. Here's what we do in this module. In a previous module, we looked at a fragment of English, and remember it was a stylized, somewhat artificial style of English, and a very simple one, where our noun phrases, the only kind of noun phrases we considered were noun phrases that had proper names in them. Okay, so we have the words, the proper names Hema, Shahrukh, Raj, and so on. And that's obviously a very small part of English. Those are not the only kind of noun phrases you find in natural languages. The noun phrases that we considered in that module are what we call referential noun phrases. Referential noun phrases because they can be taken to denote, in some sense, objects or persons, individuals or things. That's what they look like. However, there is also another class of noun phrases that we call quantified noun phrases. And natural language is full of these, and they cannot quite be given the same kind of semantics that referential noun phrases have. What are quantified noun phrases? Well, these are noun phrases that typically contain a determiner, words like the, and so on, the two articles that you're familiar with, but also other determiners or determiner-like expressions like every, some, and so on. Now, before we move on, we might want to spend a little bit of time thinking about why these noun phrases cannot be taken to be object denoting. So consider a quantified noun phrases like some woman. Let's use it in a sentence like some woman is blonde. Let's say we say some woman is blonde, and then we say some woman is red-haired, and compare that with the sentence some woman is blonde and red-haired. Now, contrast this with the same kind of examples, but the sentences now have proper names instead of some woman. So let's say we say Hema is blonde, Hema is red-haired, and compare that with Hema is blonde and red-haired. When we say Hema is blonde and Hema is red-haired, we immediately recognize that those two sentences can never be true in the same circumstance. Why is that? This is because we know that you cannot be blonde and red-haired. The same person cannot be blonde and red-haired at the same time. So, given the semantics that we developed in the module on semantic composition part 2, you know that Hema is blonde is true if and only if the denotation of blonde, the denotation of Hema, namely the person Hema, is a member of the set of those things that are blonde. Hema is red-haired is true if and only if Hema is a member of the set of those things that are red-haired. But if the set of red-haired things and the set of blonde things are mutually exclusive, that is, they have no member in common, Hema cannot be a member of both of them. Now, when we reasoned about this, the only thing we found that was relevant was the fact that Hema is object denoting. Hence, the fact that these two statements are contradictory depend on A, the fact that Hema, the noun phrase Hema, is object denoting, and the fact that to be blonde-haired and to be red-haired are mutually exclusive properties. Now compare this with the previous examples I just cited. Some woman is blonde, some woman is red-haired. Intuitively, we know, it's a linguistic fact, that these two sentences are not contradictory, right? So it is perfectly possible for us to be in a situation where some woman is blonde is true, some woman is red-haired is true, even though the property to be blonde and to be red-haired are mutually exclusive. This means that some woman cannot be object denoting, because if it were object denoting, it would denote an object. For the first sentence to be true, it had to be a member of the set of blonde things. The same thing also had to be a member of the set of red-haired things for the second sentence to be true, and yet the same thing cannot be in both of those two sets. Okay? And yet the two sentences that I just cited are not contradictory. This means you can also come up with similar arguments to show that noun phrases like every dog, every man, and so on also cannot be object denoting. To just give one example, suppose I said every dog is red and compare that with every dog is not red, and form their disjunction. Either every dog is red or every dog is not red. Okay? Now, compare this every dog is red or every dog is not red is a statement that can be true in some circumstances, but it could also be false in other circumstances. Now compare this with the sentences Hema is red and Hema is not red. Hema is red or Hema is not red is a tautology. It is always true because the set of red things and the set of not red things jointly exhaust all the possibilities that you can imagine. And so Hema has to be either in one or in the other, which makes Hema is red or Hema is not red a tautology. But every man, every dog is red or every dog is not red is not a tautology. Again, what this shows us that every dog cannot be object denoted. Now that we have decided, now that we have seen that quantified noun phrases cannot be object denoting, is there anything that we can say about quantified noun phrases? Now, there are various ways of look at the semantics of quantified noun phrases like this. There is one way of looking at the semantics that we will treat in two other modules that will come much later. There's one on generalized quantifier theory 1 and generalized quantifier theory 2. We'll see those. But for now, let's consider one way of looking at the semantics of these sentences. Whenever we use quantified noun phrases in a sentence, so let's take something like every dog has a tail. Okay, how can you think about the semantics of this sentence? What exactly does the semantics say? Okay, why can every dog not be object denoting? Can it be related to statements where something that you have instead of every dog are object denoting? So what do we mean when we say every dog has a tail? What you're basically saying is the following. Okay, imagine all the dogs somewhere. Okay, I point to each dog and say, this has a tail, this has a tail, this has a tail, and so on. Okay, so in other words, you can think of the statement every dog has a tail as being composed of two parts. It's composed of a noun phrase, every dog, and another sentence that is a full sentence, but instead of a subject, you have something like a pronoun. So it's something like every dog, it has a tail, okay, where it is a pronoun. Now think about the meaning of pronouns. What's the semantics of pronouns like? We won't discuss the semantics of pronouns in great detail, at least from a natural language standpoint yet. But if you think about the semantics of pronouns, what do we mean when we use a pronoun in a sentence? Suppose I say something like, he left or she left. A pronoun is it denotes an object just like proper names like Hema or Shahrukh or Raj do. However, its reference, the thing that it refers to, is context dependent. So when I use he left, the semantic value of he will depend on certain kinds of acts that I might perform. What kinds of acts might this be? Suppose the core use of a pronoun is, let's say I point to someone, to a person, to a male person, and say, he is about to leave. You know that the referent of he is that person that I pointed to. Sometimes you can also guess what the referent of a pronoun is if there is some contextual information that allows you to infer what the referent is. So for example, imagine I'm teaching a class, a male student gets up and leaves, and I just, looking at the class, I just say, he left, okay? Now, everyone in the class will immediately recognize that when I said he, I was referring to the person who just left the class, okay? So there is an intimate connection between quantified statements and pronouns, that what you have in quantified statements is some kind of connection to an element in a sentence which is object denoting, but its value is context dependent, unlike that of a proper name. So when I use a proper name like Hema, it refers to a particular individual, and that's that, okay? You don't need further contextual information the way you do with pronouns. So this is the basic intuition that we will start with when we talk about the semantics of quantified statements. Now, here's the tactic we will adopt. In this module, we won't directly talk so much, we won't directly deal with so much about examples from natural language with quantified statements, with quantifiers that contain words like every, some, and so on. Instead, we will look at an artificial language. This is an artificial logical language that has been developed, that was developed in logic and mathematics in the late 19th and early 20th centuries, in order to formalize earlier versions of logic that had been around, okay, with some further innovations that made them quite different from the earlier versions of logics that you had before. Now, whereas even though this language that we will talk about is an artificial language, it nevertheless has some connection to quantified statements that we find in natural language. And its connection with natural language we will explore more directly in the next module, which is called Quantification Theory, Part 2. So predicate calculus is a language of logic, is a language that's common in logic, and it has applications in mathematics and a variety of other fields, is the basis for much work that is done in many of these areas. What we will do, what we analyze in predicate calculus are expressions of an artificial language that bear a certain relationship to statements that you find in natural language with quantified noun phrases. We will look at the syntax of the predicate calculus. Then we will also look at the semantics of the predicate calculus. Now, what does the semantics of the predicate calculus look like? The predicate calculus has a syntax that is formed from the following basic units. You have symbols for predicates, you have symbols for terms, you have symbols for constants, you have symbols for variables, you have symbols that are called connectives, and then we have symbols for quantifiers. Another rule that we need to consider that says basically that form that pred1, pred sub 1 goes to PQ, pred sub 2 goes to K, pred sub 3 goes to G. Now, what this means is that we are operating with a system where you have a one-place predicate, a two-place predicate, where you have some one-place predicates. You have a two-place predicate, you have a three-place predicate. A one-place predicate combines with one term to give you a formula. A two-place predicate will combine with two terms to give you a formula. A three-place predicate will need three terms to give you a formula. Now, this syntax of the predicate calculus generates all kinds of expressions. So you can say, for example, Px1 is a remember, P is a one-place predicate, x1 is a variable, it's also a term, therefore Px1 is a formula. Px1 and K x1, x2, remember K is a two-place predicate, it needs two terms, so it can combine with x1 and x2, which are two variables, and remember variables are terms, so K x1, x2 is also a formula. And if you follow the rules, you will notice that Px1 and Kx1, x2 is also a formula. Now, if you put a negation in front of this, this is also a formula. Now, if you put for all x1, which is a quantified expression, what you get is also a formula. Now, you can have derivation trees for formulas of predicate calculus, just as you have derivation trees for, if you follow the syntax of a natural language like English. You've seen examples of this in the previous module on semantic composition. Now, there is one basic notion that is fundamental. This is that is fundamental in the predicate calculus. This is the distinction between free versus bound variables. You all know basic syntax. You all know what C command or constituent command means. In a syntactic tree, we say that a node A C commands a node B if and only if the first branching node that dominates A also dominates B. We use the same notion here. A variable is bound if and only if there is a quantifier followed by an instance of the same variable that C commands this in a formula. A variable is free in a formula if and only if there is no such quantifier. So if you have a formula that says for all x1, P of x1, the x1 in the formula is bound by the quantifier for all x1. Remember that the same variable can appear in more than one place in a formula. We use the term occurrences of variables for these different times the variable occurs in a formula. You can have a formula in which one occurrence of a variable is bound, but the other occurrence is free. So for example, if you look at a formula that says for all x1, Px1, brackets, and Kx1, x2, the first occurrence of the variable x1 is bound, but the second occurrence of the variable x1 is free because the first universal quantifier doesn't C command the second occurrence of the variable. Remember, when you are looking for the freedom or bondage of variables, you must make sure that the quantifier that C commands be followed by the same variable. So if I have a formula that says for all x2, p of x1, the quantifier for all x2 does c-command the variable x1, but the x1 is not bound because the variable that comes right after the quantifier is x2 and not x1. That's what you need to keep in mind. Now let's look briefly at the semantics of the predicate calculus. In order to interpret expressions of first-order predicate logic, we use something that we call a model. A model is an ordered pair consisting of a universe of discourse, this is a universe of things, and something that we call a valuation function. A valuation function assigns values to the basic expressions of your logical language. The valuation function assigns values to names. It will assign values to the predicate letters. A one-place predicate letter is assigned a set of things taken from the universe of discourse U. The valuation function assigns to a two-place predicate a set of ordered pairs of things taken from your universe of discourse. A three-place predicate is assigned a set of ordered triples of things that are taken from your universe U. Now, what do the semantic rules look like? Now, here is briefly I provide the basics of the semantics of the predicate calculus that you will see there. It requires, among other the one thing that you will need is a way of assigning values to variables. This is done by what are called assignment functions. We use assignment functions. An assignment function assigns values to variables. It's a function that to each variable assigns something that's taken from our universe of discourse. The rules that you see, the semantic rules that you need in order to interpret the syntax of predicate logic are what you see right there. Once we have the semantics, we can define entailment, logical equivalence, validity, contradiction, and so on. A formula phi entails a formula psi if and only if every model in which the one formula is true, the second one is also true. Formulas phi and psi are logically equivalent if and only if phi and psi receive the same values in the same models. A formula phi is valid if and only if it is always true in every model. A formula phi expresses a contradiction if and only if it is false in every model.